In this first lecture of Module 6, we will introduce the concept of buffers, or buffer solutions, which are used to control pH. It's often advantageous to run a chemical reaction in a solution that maintains a fairly constant pH, even upon addition of or production in the reaction of acidic or basic substances. To do this, we run the reaction in a buffer. Probably the most easily recognized application of buffers would be the buffer solutions present in human blood. Blood needs to be kept at a fairly narrow pH range, because if it becomes too acidic or too basic, some critical enzymes and other molecules that are needed for survival would not function. So when your body, through metabolic processes, produce hydrogen ions or hydroxide ions, these are buffered in the blood, meaning they don't change the pH of the blood very much because the blood pH is maintained by buffers. So the formal definition of a buffer would be a solution that resists significant changes in pH upon exposure to acidic or basic substances. A buffer solution is one that typically consists of significant and roughly equal quantities of a weak acid and its conjugate base, or a weak base and its conjugate acid. An example of what I would call a classic buffer would be the weak acid conjugate base buffer that has both acetic acid and its conjugate base acetate present. So in this particular example, we want to calculate the pH of a buffer that's made up of a weak acid and its conjugate base, where the weak acid is acetic acid present at 0.1 molar concentration, and the conjugate base is acetate that's introduced by making the solution also 0.120 molar in sodium acetate. So our job here is to calculate the pH of this buffer. It's always a good idea to write down a relevant equilibrium. Here it would be acetic acid and water in equilibrium with hydronium ion and acetate. And we remind ourselves that the Ka of acetic acid is 1.8 times 10 to the minus 5. And we'll deal with this as we have before by setting up an ice table, and we can begin to fill in the ice table. It claims in the problem that the concentration of acetic acid was 0.1 molar, so we'll put that in our initial row. Water, of course, we don't deal with. Hydronium ion concentration, we don't know, but we know, or we'll assume, it's close to 0 to start with, and the concentration of acetate would be 0.12 molar. You should note here that we made the solution 0.12 molar in sodium acetate. That was the way we got acetate in solution. If you recall, the sodium ion is neutral, and so it's considered a spectator ion here. So if we filled in the change row, we would see that the reaction would go to the right to reach equilibrium, and so the equilibrium row would look like this, and we could then do the usual math, set up an equilibrium constant expression with the expressions for the equilibrium concentrations written in the appropriate places. We could then decide we were going to solve for x by using the quadratic. I often partially solve this by hand on these slides, but of course the easiest thing to do is just put this in Wolfram alpha. In fact, you remember, you can just put the original equation in Wolfram alpha. You don't have to hand calculate to this point. In any event, X turns out to be quite small, and it is equal to the hydronium ion concentration according to our ice table. If you calculated the pH based on this hydronium ion concentration, it turns out to be 4.82. So the pH of our 0.1 molar acetic acid, 0.12 molar acetate buffer is calculated to be just that, 4.82. So the job of this buffer would be to try to maintain a pH close to 4.82, even when we intentionally add acid or base to the solution. We'll get to doing those calculations shortly in the future. You might ask, well, how much acetic acid is left after it reaches equilibrium? Well, X is so small that essentially the acetic acid concentration hasn't changed much from its initial concentration. Obviously, it's slightly lower, or else we wouldn't have gotten enough hydronium ions to do the calculation. But it's very close to what it was initially. Same thing for the acetate ion concentration. It obviously does go up a little bit, but within a margin of error here, we can assume that it hasn't changed very much at all. So oddly enough, we can assume that the acetic acid and acetate haven't moved hardly at all from their initial values, and we say this is due to what's called the common ion effect, which we'll expand upon on the next slide. So let's illustrate what we mean by the common ion effect by doing a couple of calculations. On the left here, I have the pH of 0.1 molar acetic acid in the presence of added acetate. In other words, the pH of the buffer we just calculated on the previous slide. And there it is, 0.1 molar acetic acid, 0.12 molar in sodium acetate, our acetic acid acetate buffer. And what we'd like to do is compare the pH we get here with the pH of just a 0.1 molar acetic acid solution. In other words, we're not adding any acetate from the outside. If we do the calculation for the buffer as we did on the previous page, the ice table would look like this. The ice table for the acetic acid with no added acetate, of course, looks very similar, except we started with no added acetate. So the equilibrium row looks identical except for the fact that there's an X here under acetate rather than 0.120 plus X. Well, we solved the buffer question on the previous slide. We found out the pH would be 4.82. One thing we actually didn't show on the previous slide was a percent ionization calculation, and as you can would expect, the percent ionization is quite low of the acetic acid, 0.015%. So this reaction does go to the right, and acetic acid does ionize slightly, but not very much. Well, let's look at what we get on the right. Solving with the usual procedures, we'd find out that X is much larger and the pH is lower in this case, and therefore the percent ionization is higher. Now, it's nothing to write home about. 1.33%, acetic acid is a weak acid, but it's certainly much bigger than the percent ionization of acetic acid in the presence of acetate, presence of added acetate. So what we say here is that when we intentionally add acetate from the outside, it suppresses the ionization of the acetic acid. That makes sense, according to Le Chatelier's principle. And when you suppress the ionization of the acetic acid, it's going to have the effect of raising the pH because you won't produce as many hydronium ions. So the acetate ion is the common ion between the acetic acid ionization and the dissolving of the sodium acetate. So acetic acid by itself produces some acetate, But if you add acetate from the outside, what you're doing is you're adding an ion that's common to this equilibrium, because this equilibrium does produce some acetate, but if you add acetate, you're adding a common ion, and meaning that it's common to both equilibria, and the addition of that common ion suppresses the ionization of the acetic acid, resulting in lower ionization and a higher pH. This is just simply referred to as the common ion effect. Now there's actually an easier way to calculate the pH of buffers rather than going through the whole Ka expression and Wolfram alpha, solving for X and so forth. And we can show you that by taking the Ka expression for the ionization of acetic acid and rearranging it into an expression that we can use a little more easily to calculate the pH of a buffer. So here's our ionization of acetic acid, and here is the Ka expression, as you would expect. Let's rearrange this a little bit, and what I mean by that is that first of all, we'll take the log to the base 10 of both sides. So we have log of Ka on the left, and on the right we have log of this entire mess right here. We can expand this a little bit and keep our log of Ka, and remember that the log of this quotient is equal to the log of what was on top minus the log of what was on the bottom. We can then continue to expand and remember that the log of a product is equal to the log of the first term of that product plus the log of the second term, and then we retain the minus log here. Here we'll do a little rearranging, and you could think of this in a couple of ways. One would be that I brought log of the hydronium ion concentration over to the other side. To the left, I brought log of Ka over to the right. So we'd have minus the log of the hydronium ion concentration equals minus the log of the Ka plus these two terms here. You recall that minus the log of the hydronium ion concentration is pH, minus log of the Ka is pKa, and that log of acetate minus log of acetic acid is the same as the log of the acetate concentration divided by the acetic acid concentration. So the pH here would be the pH of our buffer. The pKa would be the pKa of the acetic acid. And for the concentration of acetate and acetic acid, we can actually use their initial concentrations, because remember, in the presence of a large amount or a significant amount of added external acetate, the ionization of acetic acid is suppressed, and so the concentration of acetate is very close to what it started as, and so is the acetic acid, so we can put the initial concentrations in here. Now, applying this new form of the Ka expression to our 0.1 molar acetic acid, 0.12 molar acetate buffer, we'd have pH of our buffer equals minus the log of the Ka of acetic acid, because that's what pKa is, plus the log of the acetate ion concentration divided by the acetic acid concentration. The pKa minus the log of the Ka is 4.74. This term would be log of 1.2, so we'd have 4.74 plus a small adjustment from this log term gives us a pH of 4.82, which was the same pH we got using the ICE table. This expression for calculating the pH of a buffer can be generalized to apply to any buffer system. And on the next slide, we'll call this rearranged Ka expression right here the Henderson-Hasselbalch equation. So this Henderson-Hasselbalch equation, as I said before, is a general expression used to calculate the pH of any buffer system. And the general form would look like this. The pH of the buffer equals the pKa of the acid form plus the log of the ratio of the base form divided by the acid form of the buffer. Recall this is the pKa of the acid form, and every buffer has an acid form and a base form. We'll try to point these out as we go along, and being able to spot the acid form and the base form of a buffer is key to getting the numbers in the right places to use the Henderson-Hasselbalch equation. For the acetic acid acetate buffer, of course, the acid form was acetic acid and the base form was acetate. This makes perfect sense. Acid has the hydrogen ion, base form does not. So let's do an example of a calculation of a pH of a different buffer besides the acetic acid acetate buffer. And this example problem says a buffer solution is prepared which is 0.150 molar in phosphoric acid, H3PO4, and 0.4 molar in sodium dihydrogen phosphate, NaH2PO4. Calculate the expected pH of this buffer. Well, I think right away you could determine that probably the acid form is H3PO4, and the base form will turn out to be H2PO4 with a minus charge. That would be the anion that comes out of this ionic compound. So we'll write an equilibrium showing this system acting as a buffer, meaning we've got the acid form here, phosphoric acid plus water, phosphoric acid losing an H plus to water to form hydronium ion, and then the H2PO4 minus ion being left. And we have 0.150 molar of our weak acid, phosphoric acid, and we have 0.4 molar of our conjugate base, H2PO4 minus. Our conjugate base, of course, is our base form. And as before, sodium ion is a spectator here. We're just using the anion from this ionic compound that was added. So we have significant and roughly equal amounts of both the acid form, that's the phosphoric acid, and the base form, dihydrogen phosphate. That means this qualifies as a buffer system. Let's employ the Henderson-Hasselbalch equation. pH equals pKa plus log of the concentration of the base form divided by the concentration of the acid form. And this would be minus the log of 7.5 times 10 to the minus 3 because that number is the Ka1 of phosphoric acid. And that would give us the pKa, of course, then is 2.125. And the dihydrogen phosphate concentration is 0.4. The phosphoric acid concentration is 0.15. So we have the log of 0.4 divided by 0.15, log of that ratio. And that would be equal to 2.125 plus 0.426, which would be 2.55. I may not have been as careful as I should have been with brackets here. I want you to remember that this is the log of this whole ratio. It's not the log of 0.4 divided by 0.15. It's the log of this whole ratio. I could have put brackets around 0.4 divided by 0.15. Let's look at a second example. Suppose a buffer solution is prepared, which is 0.15 molar in sodium dihydrogen phosphate and 0.4 molar in sodium hydrogen phosphate. Calculate the expected pH of this buffer. Well, this looks suspiciously similar to the first example that we did just on the previous slide, the example number 1. But there is a difference. Now, as before, we want to write an equation showing that this is indeed a buffer solution. So let's do that. We have dihydrogen phosphate from the sodium dihydrogen phosphate, and it's present at 0.15 molar concentration. We're going to label that as our weak acid because the other form present is 0.4 molar hydrogen phosphate, which is the base form of dihydrogen phosphate, and this hydrogen phosphate is also added as an ionic compound, an ionic salt. And again, the sodium ions released here when this dissolves are not a factor here. They're neutral spectators. So our equilibrium here makes sense. We have the acid form plus water giving the base form plus hydronium ion. Again, we have an acid form and a base form. Now, the curious thing here is that what was the base form in the previous example, which was this, is now the acid form or the H plus donor in this buffer. That's okay. H2PO4 minus is capable of either taking or giving hydrogen ions. So we have here significant and roughly equal concentrations of something acting as a weak acid, H2PO4 minus, and something acting as a base, HPO4 2 minus. Let's use the Henderson-Hasselbalch. We have the pKa, or minus the log of the Ka of dihydrogen phosphate. Remember, this is simply the Ka2 of phosphoric acid, and it can be found in tables of Ka values for polyprotic acids. Now, don't be shocked if you use a table that's different than the ones that I supply from textbook or other sources. Reported Ka values for some acids do differ depending on the source of the information. So the source I'm using uses this, so that's what we'll use. The pKa turns out to be 7.208, and then we have the concentration of the hydrogen phosphate, the base form, and then the concentration of the acid form. We take the log of this whole ratio here, and we get 0.426 and add it to our pKa, and we get a pH of 7.63 for this buffer, which is significantly different than the phosphoric acid dihydrogen phosphate buffer on the previous slide. Let's do one more example here of the actual calculation using the Henderson-Hasselbalch. Suppose we prepared a buffer by taking 6.419 grams of ammonium chloride and dissolved it straight into 400 milliliters of 0.2 molar aqueous ammonia. We're going to assume that there's no significant change in volume from the dissolving of this much ammonium chloride. So we have 400 milliliters of solution. We want to calculate the expected pH of this buffer. Well, again, let's write an equilibrium. Well, the equilibrium we're going to write is the equilibrium between ammonium ion and ammonia. Ammonium ion plus water, giving ammonia plus hydronium ion. Our source of ammonium ion is the ammonium chloride, and our source of ammonia, of course, is the ammonia solution that we dissolved our ammonium chloride in. Well, we have 0.3 molar ammonium ion, and we can show how we got that. We got that by simply calculating how many moles of ammonium chloride we added and dividing by the volume of the solution. Now remember, chloride is a neutral spectator. Chloride is the conjugate base of the strong acid HCl, and it's neutral in solution. So here the anion chloride is just a spectator, and our source of ammonium ion is ammonium chloride. Well, we also know that ammonia is present at 0.2 molar concentration. So of course now we have the weak acid ammonium ion and its conjugate base ammonia. So we have the acid form and the base form present. And they're present in roughly equal concentrations and significantly high concentrations. And so this qualifies as a buffer system. Let's use the Henderson-Hasselbalch. Well, the key thing to remember here is that the pKa means the minus the log of the Ka of the acid form of the buffer. So sometimes you would have difficulty finding the Ka of ammonium ion in typical tables. And as you recall, we could calculate the Ka of the ammonium ion from the Kw divided by the Kb of ammonia. And the Kb of ammonia is something that you can find easily in tables of Kb values. And we find that the Ka of ammonium ion that way is 5.56 times 10 to the minus 10. So we put it here. And so the pKa of the ammonium ion is 9.255. And now we simply slip the base form concentration in this log term divided by the acid form concentration. We get the log of 0.2 divided by 0.3 of that ratio. Again, remember, I was sloppy and didn't put brackets around that. In any event, we have 9.255 now minus 0.176 from this log term because it's the log of a number that's less than 1. And we get a pH of 9.08 for this buffer. Now, an additional note about using the Henderson-Hasselbalch equation. It is possible, instead of using molarities in that log term, to just use moles of the acid form in moles of the base form. We can illustrate this by looking at example 3 from the previous slide, this exact same example, only this time in the Henderson-Hasselbalch equation we'll put moles and not molarity. Now to get the number of moles of the acid form, of course, you would just calculate how many moles of ammonium chloride that you added, and it turned out to be 0.1200 moles. And the number of moles of base form would be the volume of the ammonia solution times the concentration, and we'd get 0.0800 moles of the base form. And so when we write our equilibrium, instead of molarity underneath the ammonium ion and the ammonia, we have the number of moles of each. And if we use the Henderson-Hasselbalch equation, notice the base form is now in moles instead of molarity, and the acid form is in moles rather than molarity. Everything else is the same. pKa is still 9.255, and we take the log of 0.08 divided by 0.12, and surprise, surprise, we get the exact same result we got when we use molar concentrations of ammonia and ammonium ion. Now you might ask, is this even worth noting? And of course, yes, it's quite important. And the reason is that when we get to the point where we look at the effects of adding strong acid or strong base on a buffer system, it's often much easier to calculate changes in pH by tracking moles, that is by counting, rather than tracking concentrations. So again, in future lectures, we're going to set up a buffer system, get a pH, and then we're going to add some acid and say, how much does the pH change? How well is the buffer resisting that pH change? Or we'll add some base, some hydroxide ions, and we'll see how well the buffer is resisting that. And when we do that, it's much better to work in moles rather than in molarity. Okay, last slide here. Let's summarize. Buffers are meant to control the pH of a system and consist of either a weak acid and its conjugate base, or a weak base and its conjugate acid, each present in significant and roughly equal amounts. Now, if properly prepared, buffers will resist changes in pH from added strong acids and bases. Again, I noted earlier, it doesn't mean the pH won't change, it's just that it won't change very much. Let's summarize the buffers we worked with in this lecture. The first was the acetic acid acetate buffer. The second was the phosphoric acid dihydrogen phosphate buffer. The third was the dihydrogen phosphate hydrogen phosphate buffer. And the fourth was the ammonium ion ammonia buffer. Let's look at the acetic acid acetate buffer. The the acid form, of course, was acetic acid. The pKa of that acetic acid was 4.74. The base form was, of course, acetate, and the source of that acetate was sodium acetate. The base form to acid form concentration ratio was this. pH turned out to be 4.82. For the phosphoric acid dihydrogen phosphate buffer, the acid form was, of course, phosphoric acid. The pKa of that acid form was 2.125. The base form was dihydrogen phosphate, and the source of that was sodium dihydrogen phosphate. The ratio of base form to acid form was this, and the pH was 2.55. For the dihydrogen phosphate hydrogen phosphate buffer, the acid form was dihydrogen phosphate. The source, again, was sodium dihydrogen phosphate. Again, note that the acid form in this buffer was the base form in this buffer. The pKa of the acid form here is 7.208. The base form would be a form with one less hydrogen ion, HPO42-, and the source was sodium hydrogen phosphate. The base form to acid form concentration ratio was again 0.4 to 0.15. The pH was 7.63. The ammonium ion ammonia buffer, of course, the acid form was ammonium ion and the source was ammonium chloride. The pKa was 9.255. The base form was ammonia. The base form to acid form ratio was 0.2 over 0.3, and the pKa was calculated, or the pH was calculated to be 9.08. So what's interesting about this is that you can see in just these four examples that it's possible to produce buffers of a wide range of pHs. So if you needed to protect the pH around 2.5, you could use this buffer here. If you needed to keep or protect the pH around 4.8, you could use this buffer. And you could make buffers that maintain basic pHs as well as acidic pHs. It's good to note that the pH of a buffer is determined pretty much by the pKa of the acid form, modified slightly by the base form to acid form ratio. So in the acetic acid acetate buffer, the pH is quite close to the pKa of the acid form. Same thing for each of these buffers. So the buffer is going to, pH is going to be equal to or close, either slightly higher or slightly lower than the pKa of the acid form of that buffer. There's a large number of conjugate acid-base pairs available. That means buffer solutions can be prepared with a range of pH values. And again, a properly prepared buffer will have a pH value that is within plus or minus 1 unit from the pK value of the acid form. So you notice that the pHs of these buffers are all easily within plus or minus 1 of the pKa of the acid form. That's important to remember when you start out to try to pick an acid form, base form system for a particular target pH.